Okay, so for our final application of electrostatics, we want to talk about the phenomenon of electromagnetic shielding. And so before I talk about it, I need for you to watch the video here. So see Faraday cage on YouTube. You can find multiple videos of this. And so the one that I wanted you to watch was, it's going to have a picture, or it will have a guy inside of a electrical cage, and then they're going to shoot bolts of electricity at him. Okay, so did you find something like that? All right, what happened to the guy? So was he French fried? No, so he's perfectly okay. So if you are inside of a metal object, you're going to be okay from the effects of external electricity. So in this picture here, it shows a metal ball, and then the metal ball is in the middle of an electrical field. So the electrical field is going in this direction, and remember that lightning bolts follow the direction of the electric field. So that's what a lightning bolt does. So that out here you've got a tremendous electrical field, and you've got lightning bolts, and they're going to be striking this piece of metal. So the question is, what is going to happen? Okay, the piece of metal is going to be made of, it's going to have metal atoms that have electrons that can jump from atom to atom. So metals are good conductors of electricity. So that what will happen is the atoms that make up the piece of metal are going to sense this external electrical field, and they're going to rearrange their electrons so that electrons are going to flow through the piece of metal over to this side of the piece. And then on this side you have the absence of electrons, and so that's going to make positive charges. So the charges are going to flow in response to the external electrical field. Now, what difference does that make? So remember that if you were to take a teeny tiny positive charge, it's going to be repelled by these and attracted by these, so that inside the piece of metal another electrical field is going to be generated. But what do you notice? This electrical field is in the opposite direction to this electrical field here. And it turns out that this electrical field will be equal and opposite to this electric field here. So when you add equal and opposite, the net electrical field is going to be 0. So E, and then we need to put the word net. So the total electrical field inside the piece of metal is going to be 0. It generates its own electrical field, which is equal and opposite to this one. The two of them cancel out inside the piece of metal, and so that's the reason why you don't have to worry about being electrocuted if you're inside of your car. It's not the rubber tires. So a lot of people think that you're safe inside of your car because of the rubber tires. Now, rubber is a good insulator, but during a thunderstorm, it's going to be wet. And wet rubber can carry electricity. So it's really the fact that it's made of metal is the reason why you're going to be protected. Similarly, if you are in your car and let's say there's a power pole and it falls, and so you got this electrical wire on top of your car so that your car is at 10,000 volts, do not step out of the car. Okay, as long as you're inside the car, you're okay, because the car is going to set up an electrical field that's going to cancel out the electrical field caused by that power line. But if you step out of the car, you're going to ground yourself, and then electricity will flow through your body. We'll learn more about that in our next lesson. Okay, now if you want to do it, this is a worksheet from Paul Hewitt on electrostatics, and so again, you can't read it, but if you blow up the picture, you can look at it and you can see if you can answer those questions dealing with electrostatic polarization. So let's take one more break, and when we come back, we'll take our lesson quiz.